As the 1970s progressed, CPU design became more advanced with faster clock speed, greater address capacities, and more complex instruction set. By 1972, Intel introduced the AD08, an 8-bit successor to their 4-bit processor line. This new processor featured 14 bits of address capacity, a larger instruction set, additional registers, and improved memory access. But beyond its technical specification, the AD08 was part of the most pivotal moments in computing history. Shortly after its release, two teenagers from Washington, Bill Gates and Paul Allen, used the AD08 to build a computer that would analyze traffic data for the Washington State Highway Department. This venture, named Trafodata, was a modest success and set the stage for the next project, the founding of Microsoft. This AD08 introduced significant advancement, including indirect addressing with direct addressing. A memory location is specified and the data from that address is retrieved. In contrast, indirect addressing uses the content of the reference memory location to point to another address where the data is actually stored. This capability enabled more sophisticated software techniques, such as using a vector table to map numbers to memory locations, allowing for the random selection and processing of data like sentences. Another key feature of the AD08 was introduction of interrupts, which allowed hardware signals or internal CPU events to pause program execution and jump to a high priority region of code. This capability made the CPU more responsive to external events such as mouse movement or keyboard inputs. Interrupts are still fundamental to how modern device drivers work. The AD08 designs laid the groundwork for modern desktop CPUs, influencing the development of later processors. In 1974, Intel released the AD80, which marked another milestone in CPU evolution. This 8-bit processor could perform limited 16-bit operation and introduce an external bus control to facilitate communication with slower memory and peripherals, improving system performance and noise immunity. Despite the AD80 success, the competition was heating up. The Zilog Z80, which was based on Intel's 8080 but enhanced by a former Intel engineer, began to dominate the desktop market. In response, Intel embarked on developing a 32-bit processor, the 88800. However, this project was overly ambitious and ultimately failed. A more practical solution came in 1976 with the development of a new project that would result in the launch of Intel 8086 in 1978, which became a significant milestone in CPU history. In 1980s, significant innovation in CPU design took place, paving the way for future advancement as software grew more complex. This era of processor evolution acted as a bridge connecting the early days of computing with the rich technological environment we experience today. Every modern computing device, from supercomputer to smartphones, shares a key feature: multitasking. This allows multiple tasks or processes to run simultaneously, even on a single CPU. In the 1960s and 1970s, multitasking began to take hold in the mainframe computing world, initially as multiprogramming. Multiprogramming worked by processing batches of programs and switching between them when waiting for hardware input over time. This evolved into time sharing, which allowed real-time switching between programs, letting each process use the CPU until it required external input. By the late 1960s, true multitasking appeared in system like DECS, PDP-6, and IBM OS 360. The concept of multitasking had a profound impact, especially with the development of Unix, which influenced almost every modern operating system. By the late 1916, true multitasking appeared in systems like DEC, PDP-6, and IBM OS 360. The concept of multitasking had a profound impact, especially with the development of Unix, which influenced almost every modern operating system. By the 1980s, the growing demand for multitasking, especially as it spread from mainframe computer to smaller system, led CPU manufacturers to incorporate multitasking support into their processors, bringing the technology to the personal computer market. In a traditional single-process environment, the executing program has full control over the CPU, accessing all available memory and hardware. However, this setup can lead to inefficient use of the CPU if a program has to wait for input for the CPU idles in a waiting loop. Additionally, errors or bugs in a program can crash the entire system. Multitasking mitigates these issues by allowing the operating system to manage CPU focus, switching between processes efficiently. Multitasking operating systems typically use their either cooperative or preemptive multitasking. Early systems employed cooperative multitasking where processes had to voluntarily give up control of the CPU. This could lead to problems if a process froze or failed to relinquish control, causing the system to crash. Preemptive multitasking, on the other hand, addresses this issue by allocating fixed time slices for each process, ensuring that no single process can monopolize the CPU. This guarantees stability and allows the system to remain responsive even if a process encounters an error. Preemptive multitasking is now the standard in most modern operating systems, offering better efficiency and stability. However, to manage multiple processes, all of them need to be kept in memory. The CPU switches between processes stored in memory, which requires a memory management unit to allocate and protect memory for each process. The MMU also ensures that the process cannot access memory allocated to another process, preventing accidental or malicious interference. Memory protection is crucial for maintaining the system stability and security. If a process tries to access memory outside its allocated space, the MMU triggers a hardware fault and terminates the process, preventing potential damage to the system. Some MMUs also support memory access privilege, which limit how processes can interact with memory based on trust levels. This is an essential feature for ensuring that critical resources remain secure from less trusted code. The core of an operating system called the kernel operates with the highest privilege level, giving it full control over the system. When a program is loaded, the kernel assigns it a lower privilege level, ensuring that the program cannot directly interfere with the system critical function for secure communication between programs and the operating system. A call gate is used, allowing controlled access to kernel function. An operating system application programming interference act as the interface between program and system resources, providing a secure and unified way for software to interact with hardware. APIs abstract the complexity of system resources, making it easier for developers to write programs without having to manage the underlying hardware directly. Some MMU designs also support virtual memory, a technique that allows the system to use storage resources as an abstraction layer for memory. Virtual memory improves multitasking by enabling programs to assume they start at the beginning of memory, even though their physical location in the RAM may vary. The MMU transparently mapped this logical address to physical memory locations, giving the program the illusion that it is using continuous memory, while virtual memory is not strictly necessary for multitasking. It enhances the overall system efficiency and flexibility. The segment memory model used the 8086 CPU is an early, simple form of virtual memory allowing programs to be loaded in different physical locations while appearing to use the same memory space. In 1981, Microsoft hired former Xerox programmer Charles Simonyi to develop a new type of productivity software, a word processor. 7 years prior, Simonyi had created Bravo, the first graphical user interface word processor for the Xerox Alto, pioneering the concept of what you see is what you get. Document editing, but partnering with another ex-Xerox software engineer, Richard Brody. Simonyi helped create multi-tool Word, which was Microsoft's inaugural word processor. Initially developed for the Xenix operating system, it would eventually launch as Microsoft Word for MS-DOS in 1983. The first demonstration copies were bundled with the November 1983 issue of PC Word, marking the first time software was included with a magazine. At the time, Microsoft Word stood out as the one of the DOS program desired to work with a mouse. Although it included many features, it couldn't render fonts and was generally considered inferior to WordStar, the dominant word processor of that era. The first version of Microsoft Word was DOS, was surprisingly compact, taking up only 150 kilobytes with a core executable being just 17,742 bytes. Fast forward to the present, and the modern feature-rich version of Word now requires at least 4 gig of disk space and 2 gig of RAM. The rapid evolution of software from basic tools to complex, visually rich products characterized the computing landscape of the 1990s and 1980s. This shift put increasing pressure on processors to handle more memory, improve computing power, and remain affordable for consumers. In the mid-1980s, as software demand grew, the push for mainstream adoption of 32-bit processor architecture began. Though 32-bit processors were costly to produce, which led to various design compromises. In 1982, National Semiconductor introduced the 32K series, beginning with the 32616, which was the first general-purpose 32-bit microprocessor. However, the chip's design flaws and failure to meet a speed expectation mean it didn't gain widespread adoption. In 1984, Motorola released the 8020, the first true 32-bit processor in the 68K series, with internal and external 32-bit data buses and a 32-bit arithmetic logic. The 68020 allowed single-cycle 32-bit operation. As processor and supporting hardware become more complex, the traditional instruction cycle, fetch, decode, and execute, became less efficient. The bottlenecks created slower external buses, especially memory, limited performance. In the 1970s. Supercomputer and mainframes began to address this with instruction pipelining, which breaks down instruction into sequential stages that could be processed in parallel, increasing efficiency. The next topic is the GPU overview. The rise of GPU computing and its evolution, especially in gaming and artificial intelligence (AI). GPUs initially designed for graphic and gaming have massively expanded in core count and parallel processing capability since the 1990s. The shift toward parallelism began accelerating in the mid-2000s with GPUs now featuring over 5,000 cores in 2018. Gaming requires complex simulation leading to the development of increasingly powerful GPUs. This computational demand has extended to AR, particularly deep learning which requires massive amount of matrix operations. GPU are perfect for this repetitive calculation driving advancement in both gaming and AI, creating a positive feedback loop. NVIDIA CEO Jensen Huang discusses how GPU computing has become essential for deep learning and how NVIDIA has focused on this area for years. Investing heavily in GPU technology, GPUs like NVIDIA Volta and Tesla V100 have dramatically improved performance, with the Tesla V100 achieving up to 100 teraflops in machine learning tests. These advancements are due to specialized hardware like tensor cores and software optimization, resulting in significantly higher performance and efficiency. While the Tesla V100 is designed for data centers and is priced at $70,000, it represents the cutting edge of GPU computing for business and startup. Next topic is the SUP1 operation, which is simple as possible one computer. SUP1 is a basic educational model of a computer architecture that is designed to demonstrate how a computer central processing unit operates. It is a simple 8-bit microprocessor design that includes the fundamental operation seen in real-world computers, and its primary purpose is to help learners understand how computers execute instruction, manage memory, and perform basic computational tasks. The key operations in SUP1 include the following. Number 1 is the fetch operation. The first operation in the execution cycle involves a CPU retrieving or fetching an instruction from the memory or RAM. The address of the instruction to be fetched is stored in the program counter, and the instruction is fetched from that location. It is then placed into the instruction register. Number 2 is the decode operation. After fetching the instruction, the next step is to decode it. The control unit decodes the instructions stored in the IR to determine what action needs to be performed, such as adding numbers of moving data, execute operations. Number 3 is the execute operation. Once the instruction is decoded, the CPU performs the operation specified by the instruction. For example, if the instruction is to add two numbers, the CPU retrieves the necessary data from the memory, perform the addition, and stores the result in the accumulator or another register. Number 4 is the store operation. After executing the instruction, the result may need to be stored back in memory or a register. This operate writes the result to the specified memory location or register. These operations follow a cycle known as fetch, decode, execute, store, which is the basic sequence of instruction processing in SUP1. The components of SUP1 include program counter. The program counter holds the address of the next instruction to be executed. Instruction register stores the current instruction being executed. Accumulator, a register used to hold intermediate result during computations. Memory store both data and instruction. Control unit decodes the instruction and generates the control signal to guide the CPU's operation. Arithmetic logic unit performs arithmetic and logical operations. Registers provide temporary storage for data used in operation. For example, if the goal is to perform an add operation, this step will be as follows. First, the CPU fetches the add instruction from memory using the program counter. Then the CPU decodes the add instruction, determine it is an arithmetic operation. Next, the CPU executes add operation using the ALU, adding the values from the accumulator and the memory location. Finally, the CPU stores the result back into the accumulator or memory. SAP1 serves as the fundamental educational tool for understanding the basic function of a CPU. It effectively demonstrates how simple instructions are fetched, decoded, executed, and stored in memory, providing learners with the foundational concept applicable to more complex computer systems. And last topic is the SAP programming. SAP programming refers to the development and customization of application and processes within the SAP system, application, and product and data processing ecosystem. SAP is a suite of enterprise resource planning software used by the business to manage a wide variety of processes, including finance, logistics, human resources, and supply chain management. SAP programming primarily involves using ABAP, Advanced Business Application Programming, which is SAP's proprietary programming language. ABAP is used to custom reports, interface forms, and application to meet the specific needs of business or using SAP software. Number one, here's the general details. SAP programming refers to creating, modifying, and customizing application and processes within the SAP environment using language like ABAP. It involves working with SAP modules, enhancing system functionality, developing interfaces, creating reports, and building custom solution to meet the unique needs of a business. The programming ensures that the business can tailor their SAP system to their specific operational requirement and workflows. And that's all for today.